Hello, viewers. In today's session, we are going to discuss one important problem from direct delta function, right? So here in this session, we are going to solve this integral in which we have the limits minus infinity to positive infinity, log of 1 plus x cube sine pi x over 2, and the Dirac delta function of x cube minus 1, right? So here the argument is a function that is a cubic function x cube minus 1, right? So we'll see how we can evaluate these kind of integrals involving the Dirac delta function, in which we have a function in the argument of delta function, right? So let us start. So to evaluate these type of integrals, what we do, we use an important property of Dirac delta function, right? See, suppose we have an integral, say minus infinity to infinity, and here we have some function, say f of x, and here we have delta of g of x dx. Then delta of g of x can be written as delta of gx, and here we can have sigma I is equal to 1 to n delta of x minus xi divided by the absolute value of g prime of xi, right? So whenever we have to evaluate an integral of this kind, in which we have a function inside the Dirac delta notation, then the delta of g of x can be given by this formula, right? And here xi's are the roots of the equation, that is g of x is equal to 0, right? So what we do, we solve the equation g of x is equal to 0, and xi's are the roots of this equation, right? And then we find the derivative of g of x, and we calculate g prime of xi, right? Where this I, it runs from 1 to n, right? So here we are considering the n roots of the equation g of x is equal to 0, right? So now if we compare this integral with this one, then this is our function f of x, right? Log of 1 plus x cube sine pi x over 2 is our function f of x, and g of x is equal to x cube minus 1, right? So now what we will do, we'll solve this equation g of x is equal to 0. So we have x cube minus 1 is equal to 0. So this is a cubic equation and it has three roots. So now this equation x cube minus 1 is equal to 0 has three roots, and if we factorize x cube minus 1 cube, then we have x minus 1 x square plus x plus 1 is equal to 0, right? So we have x minus 1 is equal to 0, and x square plus x plus 1 is equal to 0. So from here we get x is equal to 1, and this is a quadratic equation, so it has two roots, but we can easily see that this quadratic equation has complex roots, right? So here we'll omit or will neglect the two roots which are complex, because the discriminant of this equation is negative, right? So we'll consider only x is equal to 1, right? So x is equal to 1 is the only real root of this equation x cube minus 1 is equal to 0. So now the next step is to get the derivative of g of x, right? That is g prime of x. So the derivative of g of x is g prime of x, which is equal to 3x square, right? Since we have only one root here, that is x is equal to 1, so we can denote this root by x1, that is equal to 1, right? So we'll find out the absolute value of g prime of x1, because here we have the value of I is equal to 1 only, because we have only one root, right? So the absolute value of g prime of x1 implies that is mod of g prime of 1. So we have mod of g prime of 1. G prime of 1 can be obtained by taking x is equal to 1 here. So we have 3 times 1 square. So we have here 3, that is equal to 3. Mod of 3 is equal to 3, right? So now we have to apply this property, right? So delta of gx. Now delta of gx is equal to sigma of I is equal to 1 to n, but here we have only one root, so we have the value of I is equal to 1, right? So we can write delta of simply delta of x minus x1 divided by mod of g prime of x1, right? Okay, so we have delta of x minus x1. X1 is 1, because we have the only one root, that is x is equal to 1. So here we have 1, here we have mod of delta prime of 1, and here we have delta of x minus 1, and mod of g prime of 1 is equal to 3, right? So delta of g of x, it implies delta of x cube minus 1 is equal to delta of x minus 1 over 3. So now let us substitute this value in this integral. So now let us take this integral as I. So we have I is equal to integral from minus infinity to infinity log of 1 plus x cube, and here we have sine of pi x over 2, and delta of x cube minus 1 is delta x minus 1 over 3, and here we have dx, right? So let us take this 1 over 3 outside the integral. We have 1 over 3 minus infinity to infinity log of 1 plus x cube sine pi x over 2, and here we have delta of x minus 1, right? Okay, so now to evaluate this integral, we'll make use of the definition of Dirac delta function. So now the Dirac delta function is defined by this integral, that is minus infinity to infinity. If we have f of x, a delta of x minus a dx, then the value of this integral is equal to the value of this function at this point, that is x is equal to a, right? So this is f of a. So this is our basic definition which may be utilized to evaluate this integral. So here what we can do, we'll take this function as f of x, right? And here delta of x minus a, so our a is equal to 1, right? So now we have 1 over 3, we have the factor 1 over 3, and then we have log of 1 plus x cube sine pi x over 2, and we have to evaluate this entire expression at x is equal to 1, right? Because integral minus infinity to infinity f of x delta of x minus a is equal to f of a, because we know that the value of the Dirac delta function is only at this point, that is x is equal to a. So the spike, it exists only at this point x is equal to a, and at all other points the delta function is 0. So now if we take x is equal to 1 here, then we have 1 over 3 log of 1 plus 1 cube sine of pi by 2 times 1, right? Okay, so this is 1 over 3. Then we have log of 1 plus 1, that is log of 2. And here we have sine pi by 2, and sine pi by 2 is equal to 1, right? Because sine 90 degrees is equal to 1. So here we have 1. So this is 1 over 3 log of 2, right? So viewers, the value of this integral is equal to 1 over 3 times the natural log of 2. So viewers, this is how, by making use of this important property of Dirac delta function and the definition of Dirac delta function, we can evaluate or we can compute the values of these type of integrals. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from Dirac delta function, right? So viewers, we have already uploaded a number of problems related to Dirac delta function in our previous lectures. So here in this session we are going to discuss this important integral, right? And this integral is going to utilize some important properties of delta function. So here we have to evaluate the integral from minus infinity to infinity e raised to x cosine of pi x over 3, and the Dirac delta function 4x square minus 1, right? So here we see that we have a function, a quadratic function inside this delta function, right? Or in other words, we can say that here we have the Dirac delta function whose argument is a quadratic polynomial. So we'll see how we can solve these kind of integrals in which we have a function as an argument in the Dirac delta function, right? So let us start. So here we'll go step by step. So let us first take this integral as I, right? Now see, here we have 4x square minus 1. So whenever we come across with the Dirac delta function integrals in which the argument is a function, then what we usually do, let us take this function 4x square minus 1 as f of x, right? So the first step is to assume this function as f of x. So we have 4x square minus 1, right? Okay, now the next step is to solve this equation f of x is equal to 0, right? So we have 4x square minus 1 is equal to 0. Then we have 4x square is equal to 1. So x square is 1 over 4. So here we have x is equal to plus minus square root of 1 over 4. So x is plus minus half, right? So obviously we have obtained two roots of this equation fx is equal to 0. So let us name these roots as x1 as plus half and x2 as minus half, right? So first of all, or the first step is to do all this stuff, right? So x1 is plus half and x2 is minus half, and the next step is to see whether these the roots, it falls within the limits, that is the lower limit and the upper limit, and we can easily conclude that both these roots lie in the interval that is from minus infinity to infinity, which is our entire real number line. So once we are satisfied that these roots which are obtained by solving fx is equal to 0 lie in the interval that is lie within the limits, here the interval is minus infinity to infinity, right? Okay, now let us differentiate f of x. So the derivative f of f prime of x is equal to d by dx of 4x square minus 1, right? So this is 8x, because the derivative of x square is 2x. So we have 4 times 2x, and the derivative of 1 is 0. So we have f prime of x is equal to 8x, right? Okay, now the next step is to get the value of mod of f prime of x1 and mod of f prime of x2, right? So mod of f prime of x1 is mod of f prime of half, that is the first root, right? And mod of f prime of x2 is mod of f prime of minus half, right? Okay, so now mod of f prime of half is 8 times 1 over 2, right? Okay, so we have mod of 4, that is equal to 4. And here we have mod of 8 times f prime of minus half can be obtained by taking x is equal to minus half in this expression. So we have here minus half. So this is mod of minus 4, that is equal to 4, right? So the step is getting mod of f prime of x1, that is 4, mod of f prime of x2 is equal to 4, right? So this is the situation. Now let us write an important property of Dirac delta function. So now the important property is delta of f of x, right? See, we have taken a 4x square minus 1 as f of x. So this integral is now equal to minus infinity to infinity e raised to x cosine of pi x over 3 and delta of f of x, right? So now let us consider delta of f of x with the help of an important property of delta function. So delta of f of x is given by summation I is equal to 1 to n. Then we have here delta, that is delta of x minus xi, and here we have mod of f prime of xi, right? So this is a very important property of Dirac delta function, which is used whenever we have an argument as a function that is in this case it is a quadratic polynomial. So here we see that I goes from 1 to n, right? And these i's denotes the number of roots of this equation, that is f of x is equal to 0, right? So the number of roots of f of x is equal to 0 are n, but in this case we have only two roots, that is x1 and x2. So our value of I, it runs from 1 to 2 only, right? So now we can write delta of f of x as sigma I is equal to 1 to 2 delta of x minus xi and mod of f prime of xi. And now first taking I is equal to 1, we have delta of x minus x1 divided by mod of f prime of x1. Then since we have the summation sign, so we have here a positive sign, then delta of x minus x2 taking I is equal to 2, and here we have mod of f prime of x2. So now x1 is half and x2 is minus half, right? So here we have delta of x minus half divided by mod of f prime of x1. So mod of f prime of x1 is 4. Then we have delta of x minus x2. So x2 is minus half, so minus and minus becomes plus. So here we have half, and here we have a mod of f prime of x2 as 4, right? So the value of delta of f of x is given by this expression, right? So let us substitute this value in this integral, right? So we have I is equal to minus infinity to infinity e raised to x cos of pi x over 3, and then we have here delta of x minus half over 4 plus delta of x plus half over 4, and here we have dx. So now we can take 1 over 4 outside the integral. So now our integral is 1 over 4. Then we have minus infinity to infinity e raised to x cos pi x over 3. And then we have here delta of x minus half plus delta of x plus half, right? And here we have dx. So now let us take this function as g of x, right? So we can assume g of x as e raised to x cos pi x over 3. So now this integral I, it reads as 1 over 4 minus infinity to infinity g of x, and here we have delta of x minus half plus delta of x plus half, and here we have dx. Now we can write here two integrals. One is minus infinity to infinity g of x delta of x minus half dx plus minus infinity to infinity g of x, and then we have delta of x plus half, and here we have dx, right? So now we have to obtain the values of these two integrals, and here we'll make use of the definition of Dirac delta function. So now the definition of a delta function, it goes like this: the integral from minus infinity to infinity, and if we have some function say g of x and delta of x minus a dx, then the value of this integral is equal to g of a, right? So the delta function says that the value of the delta function, it is equal to the value of this function which is associated with delta function at this point a, right? So here we have x is equal to a, and this spike denotes the value of the delta function, right? And apart from x is equal to a, the delta function is 0 in the entire line, right? So here we have minus infinity, here we have plus infinity. So the value of delta function, it exists only at x is equal to a, and at all other points except x is equal to a, the delta function is 0, right? So the value of this integral is equal to the value of this function g of x at this point x is equal to a. So in the first integral we have x minus half, so the value of a is equal to half, right? And in the second integral we have x plus half, so the value of a is equal to minus half. So we have now 1 over 4, and the value of this integral is the value of this function at this point, that is half. And here we have the g of minus half, right? And g of half and g of minus half can be obtained by taking x is equal to half in this expression and x is equal to minus half in this expression. So now g of half is equal to e raised to half. Here we'll take x is equal to half. Then cos of pi x that is x is half, so we have simply pi over 6, right? And this is e raised to half, and cos pi by 6 is cos 30 degrees, which is equal to square root of 3 over 2, right? And g of minus half is equal to e raised to minus half, and cos of taking x is equal to minus half, we have minus pi by 6, right? And from trigonometry we know that cos of minus theta is simply equal to cos of theta, right? So cos of minus pi by 6 is simply equal to cos of pi by 6. So this is e raised to minus half. Cos pi by 6 is cos 30 degrees, that is equal to root 3 over 2. So now the value of this integral is equal to 1 by 4, and then for g of half we have e raised to half root 3 over 2, and here we have plus e raised to minus half and root 3 over 2, right? Now simplifying it, we can take root 3 over 2 outside the this factor. So we have root 3 over 8, taking root 3 over 2 common. So we have here e raised to half plus e raised to minus half, right? So viewers, the value of this integral I is given by a square root of 3 over 8 e raised to half plus e raised to minus half, right? And we can also express this expression in some other forms also. So now we know that the hyperbolic function, that is hyperbolic cosine of x, is given by e raised to x plus e raised to minus x over 2. So e raised to x plus e raised to minus x can be written as 2 times the hyperbolic cosine of x, right? Now if we take x is equal to half, in this expression we have e raised to half plus e raised to minus half is equal to 2 times cosine h times h half, right? So now replacing this expression with this one, we can now write I is equal to root 3 over 8 times 2 times the hyperbolic cosine of half, right? So this is 2 4s are 8, so we have root 3 over 4 hyperbolic cosine of half, right? So the value of this integral I can also be taken as the square root of 3 over 4, and we have hyperbolic cosine of half, right? So viewers, this is how by making use of the concept of the definition of Dirac delta function and the properties of Dirac delta function, we can evaluate these type of integrals.